Hello students, welcome to EPG Pathshala. I am Dr. Sanjay Kumar Chamoli from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about a module, nuclear force and its properties, from paper Nuclear and Particle Physics. So students, let us see what we are going to learn in this module. First thing that we are going to learn is the importance of scattering experiment in understanding nuclear force. Second thing, the importance of neutron-proton scattering and its properties. And the third thing, the importance of nuclear interaction in general. Now, nuclear force, nuclear-nuclear interaction. Now, deuteron case yields limited information about anion interaction as there are no excited states. So, interaction can only be studied in one configuration, that is L is equal to 0. So, though in the previous discussion about deuteron, we have found that it is the most simplest kind of system in which the nuclear interaction can be studied because it has only one proton and one neutron, and it has given some beautiful results which we have interpreted and came to know about after going through them, we came to know about the nature of the nuclear interaction. But the story is not complete. In order to understand the nuclear-nuclear interaction, in order to understand the nuclear force in more detail, we need to consider some other cases also, like nuclear-nuclear interaction. So why we need to consider the nuclear-nuclear interaction? Because in the case of deuteron, there is no excited state. So whatever behavior of the interaction or whatever properties of nuclear interaction we can study by studying deuteron is only in the ground state, because it has only got one configuration, that is L is equal to 0. For detailed study, nuclear-nuclear scattering experiments are needed. There are two ways to perform nuclear-nuclear scattering experiments in general. First, the incident beam of nucleons is scattered from a target of nucleus. So it means if there is a target of nucleus and the beam of nucleon hits the target, and then some scattering takes place, and looking at the results of that scattering, we can basically make out some conclusion about the nuclear interaction. So scattering of a single nucleon will include the complicated effect of multiple encounters and is very difficult to extract the properties of the interaction between individual nucleons. So this is the issue with this kind of scattering mode. Another way by which we can have the nuclear-nuclear interaction is an incident beam of nucleons is scattered from a target of hydrogen. So it means our target in this case is a hydrogen, which can be either in the form of a gas preferably, or in case of some other state of the matter. So scattered by individual, in this case scattered by individual protons, mainly multiple encounters are greatly reduced by large spatial separation between nucleons. So properties of nuclear-nuclear interaction can be deduced without complications. So now you can see the difference in the two kinds of scattering. In the first case, that there was a target and a beam of nucleon was hitting, but since the target has multiple atoms in the line, so it is difficult to have the pure kind of nuclear interaction results from that situation. But in the second case, we have a simplest target like hydrogen, and since in the gaseous form, hydrogen, the distance between two hydrogen atoms is large, so individual interactions, so properties of nuclear-nuclear interaction can be deduced without much complications. So in general, the nuclear-nuclear scattering resembles with optical diffraction. So intensity of scattered nucleons vary with distance like 1 by r square. So this is an analogy between the nuclear-nuclear scattering with the optical diffraction. So we have seen that the light undergoes diffraction. So it means whatever results we get from the diffraction of light, we get the similar kind of results for nuclear-nuclear scattering. So we can make a comparison. Like the intensity of scattered nucleons in the nucleon scattering varies with distance like 1 by r square, and the same is true for the optical diffraction of light. Second important thing is we notice is intensity of scattered nucleons depend on the angular coordinates theta and phi, and the same is true for optical diffraction. In case of optical diffraction, where the intensity of light is a function depends on the angular coordinates theta and phi. Third thing is a detector placed at a distant point records both incident and scattered beam. The same is true for optical diffraction also. Nuclear force, neutron-proton scattering. So after previous slides, we have seen that though we can get some information about the nuclear force or the nuclear interaction from the simplest case like deuteron, but for the complete knowledge of nuclear interaction, we need to have the nuclear reaction, especially the scattering experiment. The NP scattering is the simplest one, as complications due to Coulomb forces are not present. So the simplest case in which we can study the nuclear force in detail is the neutron-proton scattering. Why it is the simplest case? Because the Coulomb forces are not present. Neutron is neutral and proton is charged particle, so there should not be any Coulombic interaction, Coulomb force. In NP scattering, neutron-proton system is analyzed in the state of positive energy, that is, in a situation when they are free. This is another advantage of NP scattering. Simplest target is hydrogen gas, but nylon sheet and paraffin are also used. So in order to observe this, or in order to basically have this neutron-proton scattering, the simplest target is chosen as the hydrogen gas, but in some of the cases, nylon sheet, people have used the nylon sheet as a target and paraffin as a target, and then the neutron beam is allowed to scatter from those targets and can be analyzed. The target protons are not free but are bound in molecules. The molecular binding energy is so small, about 1 electron volt. Therefore, for the impinging neutrons of energy greater than 1 electron volt, protons can be treated as free. Now in this NP scattering, if we are going to study the NP scattering, it's very important for us to treat neutron and proton as free. Now, as we have seen that people have used hydrogen gas, the most suitable gas is the hydrogen gas that can be used as a target. But since people are using nylon sheet, paraffin and other kind of targets in which the hydrogen is not free but it is bound in the molecular arrangement, but the binding energy of the molecular arrangement in which the hydrogen are is very small, around 1 electron volt. So if the neutron beam falling on this target is having an energy greater than 1 electron volt, which is in most of the cases is true, then protons can also be treated as free. Nuclear force, neutron-proton scattering. We are continuing with our discussion about neutron-proton scattering. The presence of electrons also does not affect the process because they are too light to cause any appreciable trouble to incoming neutrons. Now remember that in the target consists of hydrogen, and hydrogen has 1 electron in the orbit. So, but electrons do not disturb the interaction process, as neutrons are the neutrons are very heavy as compared to the mass of the electron. Second thing, the neutrons are neutral and electrons are charged particles. So no interaction can happen between the neutrons and electrons. So the NP scattering is not affected by the presence of electrons. In the interaction process, some neutrons get captured and from deuteron, gamma rays are emitted. In the interaction process, some neutrons get captured and form deuteron. So when hydrogen gets combined with neutron, deuteron is formed, but deuteron is unstable in this case, so gamma rays are emitted, but the majority undergo elastic scattering. So suppose 10 neutrons hit the target, then out of 10 neutrons, only few electrons are captured by the hydrogen and deuteron is formed. whereas majority of the neutrons suffer elastic scattering and they pass. Now scattering at low energy. To solve neutron-proton scattering, so it means the neutron-proton scattering can be observed at any energy. The results of the energy range are different. Like if we study the neutron-proton scattering at low energy, the results are different than when we study the neutron-proton scattering at high energy. Now first we are going to study the NP scattering at low energy. To solve NP scattering problem using quantum mechanics, we assume the nuclear interaction by a square wave potential as assumed in case of deuteron. And contrary to the case of deuteron, here the incident particles are free, because you must remember that in the deuteron, neutron and proton are bound. But contrary to that case, here in this NP scattering, we consider the incident particles as free. That is, E is greater than 0. Nuclear force, neutron-proton scattering. So we are continuing with our discussion about the NP scattering at low energy. Now on the left hand side, a picture is shown in which the potential energy V is plotted as a function of R and the energy of the nucleus is given. So here it is shown as the square wave potential. So consider an incident neutron strikes the target on its surface with an impact parameter which is B around 1 Fermi. So impact parameter B around 1 Fermi. Impact parameter basically is the distance of line of direction of, it is the distance between the line joining the center of the nucleus, or you can in a better way you can understand that impact parameter is the distance between the line of application of nuclear beam with respect to a line parallel to it and passing through the center. And this impact parameter is a function of energy. Higher is the energy, lower is the impact parameter. So now, since we are discussing the case when the impact parameter is B around 1 Fermi, so we can calculate the corresponding energy, that what energy is required. So consider an incident neutron strikes the target on its surface with impact parameter B around 1 Fermi. If the incident particle has velocity v, its angular momentum relative to the target is mv into r. Now as we know that mvr is equal to lh bar, where L is the angular momentum. So if mvr is very much less than lh bar, then only L is equal to 0 interactions are likely to occur. So kinetic energy T is equal to half mv square, which is very much less than h bar square by 2 mr square. And if we put the values, then we get kinetic energy is equal to 20 MeV. Nuclear force, neutron-proton scattering. We are still continuing with our discussion about the neutron-proton scattering. Here in this slide, we are going to study this NP scattering problem theoretically. So Schrodinger wave equation is given by minus h bar by 2m del square psi r plus Vr psi r is equal to E psi r, where the mass appearing in the equation is the reduced mass, that is m is equal to 1 by 2 mn. Why it is m is equal to 1 by 2 mn? Because we are discussing neutron and proton and both are more or less have the same mass. So the reduced mass becomes m is equal to half of mass of either the proton or the neutron. By defining psi r is equal to ur by r, the Schrodinger wave equation is given by minus h bar by 2m d square u by dr square minus v0 ur is equal to eur for r less than capital R, and minus h bar square by 2m d square u by dr square is equal to eur for r greater than r. So it means two regions in the nucleus. Two regions means if we can assume that the nucleus has the radius r, then we have two different regions, one inside the nucleus and outside the nucleus, and another one outside the nucleus. Inside the nucleus means when r is less than capital R. The Schrodinger wave equation has the above form, but outside the nucleus, that is for r greater than r, the Schrodinger wave equation has a different form. So now for the Schrodinger wave equation inside the nucleus, the acceptable solution is UR is equal to A sine K1R, with K1 is equal to 2 square root 2m E plus V0 upon H bar. We are continuing our discussion about the neutron-proton scattering at low energy. For the region outside the nucleus, that is R greater than capital R, the acceptable solution is UR is equal to C dash sine K2R plus D dash cos K2R, with K2 is equal to square root 2me over H bar square, or UR is equal to C sine K2R plus delta, where C dash is equal to C cos delta and D dash is equal to C sine delta, and the boundary condition on U and du by dr at R is equal to R give C sine K2 R plus delta is equal to A sine K1 R and K2C cos K2 R plus delta is equal to K1 A sine K1 R. Why this boundary condition is applied? Because in order for U to be an acceptable wave function, it has to be continuous, and it has to be single valued, and it has to be continuous at the boundary. So we apply that condition. Boundary means at R is equal to R, the two wave functions should be same. So it means when we equate that, then we get these two equations. Now dividing them, we have K2 cot K2 bracket K2R plus delta is equal to K1 cot K1R. So it means we obtain, by dividing them, we obtain a relation between K1 and K2. So with the help of this relation, we can find the relation between K2 and K1. So where delta is the phase shift, given E, V0 and R, we can in principle solve for delta. Nuclear force, neutron-proton scattering. We are still continuing with our discussion about the neutron-proton scattering at low energy. In this slide, we see a picture on the left hand side, and the picture basically explains the three different regions. Three different regions means when V0 is equal to free particle, what is the situation of the wave function? When V0 is equal to minus V0, that is attractive potential, and when V0 is equal to repulsive potential. So V0 is basically, V0 is equal to 0 is the free particle, means when the potential is 0. Minus V0 is the region inside the nucleus. Plus V0 is the region, when plus V0 is called repulsive potential. It means when we are outside the nucleus, and the waveform are given. So now from the waveforms, we see a slight difference in the three situations. So if we compare them, then we see that a phase shift delta is coming into picture. The phase shift is nothing but the shift in the wave when the potential is attractive and repulsive corresponding to when the potential was 0. So in case of attractive potential, we find that the phase shift delta is greater than 0, whereas in case of repulsive potential, that is when we are outside the nucleus, phase shift delta is less than 0. So it means if V0 tends to 0, K1 is equal to K2 and delta tends to 0, a free particle solution. So it means the effect of a scattering potential is to shift the phase of the scattered wave at points beyond the scattering regions, where the wave function is that of a free particle. So this is the conclusive situation that we can understand with the help of the diagram shown. Nuclear force, neutron-proton scattering. General theory of scattering gives differential cross-section d sigma over d omega is equal to sine square delta 0 by k square. Usually d sigma over d omega varies with direction over the surface of a sphere. In a special case of L is equal to 0 scattering, d sigma over d omega is constant and the total cross section is given by sigma is equal to integral d sigma over d omega into d omega, and that gives you 4 pi sine square delta 0 by k square. So in this slide, basically tried to find out the differential cross section of scattering, NP scattering at low energy. And we have come across, if we apply a general theory of scattering, we get differential cross section of a scattering, NP scattering, as equal to sin square delta 0 by k square, and the total scattering cross section is equal to 4 pi sin square delta 0 over k square. It means the cross section of NP scattering at low energy is a function of phase shift. Phase shift is important. So L is equal to 0, phase shift is directly related to probability for scattering. So delta 0 can be evaluated from simple square well potential and compared with experimental cross section. Nuclear force, neutron proton scattering. So we are still continuing with our discussion about the NP scattering at low energy. Now in this slide, basically we would look at an example that how we can compare the low energy scattering data with the realistic estimation of cross section. Compared with low energy NP scattering data, a realistic estimate of cross section is needed. This can be obtained by putting values of all related terms. In this example, basically we have chosen the neutron energy E less than equal to 10 keV. The potential inside the potential V0 is equal to 35 MeV. From the analysis of the neutron bound state problem, we have seen that in the structure like neutron and proton, inside the neutron, the potential is of the order of 35 MeV. So here in this example, we choose that value because here in the NP scattering case also, we are dealing with neutron and proton only. So as V0 is equal to 35 MeV from the analysis of the neutron bound problem, K1 comes out to be is equal to 0.92 Fermi inverse and K2 is equal to less than equal to 0.016 Fermi inverse. So from equation K2 cot K2R plus delta is equal to K1 cot K1R, we get sin square delta 0 is equal to cos K2R plus alpha by K2 sin K2R 1 plus alpha square K2 square. Nuclear force, neutron proton scattering. So we are continuing with our discussion of the example we have discussed in the previous slide. So now we have, so in this slide basically we try to see what is the value of theoretical cross section that we can get in the NP scattering case. So cross section sigma is equal to 4 pi over K2 square plus alpha square bracket cos K2R plus alpha by K2 sin K2R. Using R is equal to capital R is equal to 2 Fermi, which is the expected value of neutron proton system, expected value of nuclear radius of a neutron proton system. Alpha is equal to 0.2 Fermi inverse. We find that K2 square is very much less than alpha square and K2 square, K2R is very much less than 1. So sigma turns out to be around 4 pi over alpha square 1 plus alpha r, that is equal to 4.6 bond. So it means if we consider a neutron-like system, neutron-like NP system, then for that system, the scattering cross section for NP scattering at low energy comes out to be around 4.6 bond. And this is the theoretical estimate. But when we plot the experimentally observed cross section as a function of neutron kinetic energy, we find that the two values do not match with each other. Implications. Experimental cross section of NP scattering is constant at low energy and decreases with E at large energy as predicted theoretically. So we have observed the NN scattering, that is nucleon-nucleon scattering, and in this case particular the neutron-proton scattering, where we had the proton target and the neutron beam was hitting the proton target and getting scattered. So the result of that NP scattering experiments, when we plot as a function of energy, then we find that experimental cross sections as a function of energy, then in that plate we notice that experimental cross-section for NP scattering is constant at low energy and decreases with E at large energy as predicted theoretically also. Second observation is scattering cross-sections depend strongly on the energy of incident neutron, because the behavior is different for different energy neutrons. Third important conclusion that we can draw from that plot, that for E less than 10 MeV, that is, if the neutron beam energy is less than 10 MeV, then scattering is essentially due to neutrons with zero angular momentum, that is, L is equal to 0, and hence in center of mass system, angular distribution of scattered neutrons is isotropic. So these are the experimental observations we have. Now, when we compare the experimental results with the theory, then we find that the observed cross-section around 21 milliband is well above the theoretical estimates, which is around 5 milliband. And remember, this 5 milliband cross-section theoretical estimate came from our understanding of nuclear interaction, understanding about the nuclear interaction from the case of deuteron. So whatever parameters we adopted to calculate the theoretical cross-section, those parameters have been taken from the case of deuteron. So the theoretical estimates are found to be quite low as compared to experimental cross-section. For the solution of this discrepancy, we must study the relative spin of incident and scattered nucleons. So it means it is in order to find an explanation for this much of discrepancy between the theory and the experiment, we need to consider the relative spins of incident and scattered nucleon. That what was the alignment of the incident neutron spin and the target nucleus spin. So student, let us summarize what we have learned in this module. The first thing that we learned is that the deuteron case is not sufficient to fully understand the nuclear interaction. Second thing, low energy scattering experiments are needed to understand the nature of interaction in multi-nucleon system. Third thing that we have understood is that in NP scattering, the scattering potential shifts the phase of the scattered wave. And fourth thing that we understood is the huge disagreement between the theoretical and the experimental scattering cross-section at low energy shows the spin dependence of interaction. Thank you.